here, and you can come up to get them here. And if you want if you have regrade requests, you have to write it on a sheet of paper and it's separate from your exam book, and then hand the request by this Friday. Okay, and then we will have a regrade for you if your request is reasonable. Yes?
How come on the first page everyone lost points for units, but on the second, third, and fourth page no one wrote in the units and no one some points?
Oh, because the exam is graded by different professors.
So there's one. Who's the professor who decided I'm going to kill people for units?
Oh, okay. I don't know. You can look at the exam book. You know, there are 4 names up there. Okay.
Is it you? This is all you're not answering.
No, 4 names here. Okay. Problem 1, problem 2, problem 3, problem 4.
Oh,
okay.
Alvarez? No, he's my homeboy. He would never do that to me.
Honestly, it says the units should be there, so you kind of look at it for more
circled
support.
I can't read.
You kind of look at there.
You can't fight it.
Yeah.
It's taking a lot.
Nothing's written in
It's like
stone.
he doesn't have any units on the next page, so
They'll take off marble.
Yeah. Somebody's gonna drop from like 70 to 30.
Man, you're the order.
Oh, you never took words, did you? Oh gosh, it was a little about it. She was like the first time I take my points.
Okay, happy April Fool's Day. Yeah, and let's hope that everything is not foolish today.
So what's our real scores for the exam?
You know, right?
That wasn't April Fool, so.
That was an April Fool.
You get 100, you get 100.
You get 100.
So let's go to section 7.2 of the textbook. I guess you have learned section 7.1. We can review section 7.1 briefly. It is where you derive Fourier transform from Fourier series. And you know that Ft is equal to, by the Fourier series theorem, equal to this number over here, whereas f sub n can be found by 1 over t dt f of t e to the minus j n omega naught t. Okay, this is from Fourier series. And that is from these 2 things, which are for periodic signal. If you have a periodic signal, I'm not very good at drawing periodic signal. Okay, this is a periodic signal. You can have this kind of Fourier series expansion. And if you make the period t going to infinity, then you have a periodic signal becoming an aperiodic signal. And then this relationship can be used for aperiodic signal as well. Yes?
Isn't it over one period?
Oh, yes. There's integration over a period. Very good. So it should be 0 to t. Okay, 0 to t. And then it can be minus t over 2 to t as well, since this is a minus t over 2 to plus t over 2 as well, since this is a periodic signal. So you let the period go to infinity. And since this is integration over a period, it doesn't matter. I can also write this integration in this manner, and it still would still be true. And if you do a change of variables, and letting f of omega be equal to f sub n 2 pi divided by omega naught, okay, where omega naught is 2 pi over capital T, is the fundamental frequency of this Fourier series expansion, then you can rewrite things so that, and then you let t go into infinity. What you get here is that this can be written as omega naught over 2 pi f of omega to the left hand side, and then you have 1 over t And if you let t go into infinity, this is going to be very, very large. Maybe I don't write t going to infinity first. dt f of t e to the minus j n omega naught t. Okay? Where you can let omega in here be n omega naught. Okay? So if you were to do this change of variables and letting t go into infinity, what you find is that omega naught over t is equal to, or omega naught over 2 pi is 2 pi over t divided by 2 pi. So it's 1 over t. So this thing essentially cancels with this thing because omega naught over 2 pi is just equal to 1 over t. And then in the limit when t goes to infinity, you have this new relationship that f of omega is equal to minus infinity to infinity dt f of t. And let me call this omega now, okay, e to the minus j omega t. Okay, so this is one new relationship that you derive when you let t be very, very large. Okay? And then the other relationship that you should derive should follow from here. Okay? And in that relationship, again, you let fn be equal to this thing over here. Okay? If you let fn be equal to omega naught over 2 pi times this, okay, which is just this quantity over here, which is 1 over t, f of omega e to the j n omega naught t, n going from minus infinity to infinity. So I just let fn be equal to this, and then noticing that fn is equal to this is the same as saying that fn is equal to this, and omega naught over 2 pi is just 1 over t, so that I can get 1 over t here. So this first relationship becomes as such, and then you can say that 1 over t can be written as omega naught over 2 pi. Just the same statement that I say here. Okay, 1 over t is just omega naught over 2 pi, and then if that is the case, then you can rewrite this as 1 over 2 pi n is to the minus infinity to infinity f of omega e to the j, and let me call this omega now, omega t, and then because 1 over t can be written as such, I can put omega naught here. What is omega naught when t becomes very large? Omega naught is a very small number, okay? So if you think of omega naught, this is 1 omega naught, 2 omega naught, 3 omega naught, I don't draw it very well, 4 omega naught. Okay, if you think of f of omega as such, then what happens is that omega naught, which is equal to 2 pi over t, becomes a very small number. Becomes a very small number as t goes to infinity. So you can think of this as in something likened to the delta omega. Okay, if it is likened to a delta omega, essentially you convert this summation into an integral, and hence you can write this delta omega is d omega f of omega e to the j omega t. And this is the second relationship in Fourier transform. Okay. So these are two very important relationships in Fourier transform. They go back and forth between each other. Okay, once you know ft, you can find capital F of omega. Once you know f of omega, the capital F of omega, you can find ft. These are called the Fourier transform pairs. Okay, and they actually follow from Fourier series. And the great thing about Fourier transform is that the signal does not have to be periodic anymore, because t becomes infinity. So you can apply it to any signal that you want, a signal that looks like that. Okay, f of t can look like that. It's not periodic, it's aperiodic, and yet its Fourier transform exists. Okay, and then we remember Passavant's theorem. Passavant's theorem says that if you were to Passavant's theorem, let me see how to spell that. P-A-R-S-E-V-A-L theorem. Okay, say that if you were to time average the power in a signal over a period, it doesn't matter, this could be minus t over 2 to t over 2, since it's a periodic signal. And what did Passavant's theorem say in Fourier series expansion that we know from here? Remember what Passavant's theorem says? Sum over
magnitude of t squared.
So Passavant's theorem says something like that, right? For Fourier series expansion. And because of this Passavant's theorem, you can also derive something for Fourier transform. If you make this relationship, you make the relationship that I can write f sub n as being equal to, let me rewrite this relationship in a simpler form. So if I rewrite this relationship, it's just 1 over t f of omega is equal to f sub n. Okay? If I rewrite this relationship with omega naught over 2 pi on the other side, if I were to insert this relationship over here, then I would have 1 over t squared, n is equal to minus infinity to infinity. Okay, f of n squared will give me f of omega squared. Okay? And then one of the t's cancel with the left hand side. So I'm left with 1 over t. So I have this, if I let t go into infinity now, if I let t go into infinity to get the Fourier transform equivalence of this, I would have f of t squared dt. And then on the right hand side, since one of the t's cancel, I would have 1 over t left. 1 over t is 2 pi over omega naught, or omega naught over 2 pi. Okay, so I have 1 over t left, so I keep 1 over 2 pi there, and then I have this left. And then I have omega naught left over there. Okay, I have this omega naught left over there, which I can write like this. But remember what omega naught is. Omega naught becomes a very small number when I let t go into infinity. And hence this can be written as an integral as well. In the limiting case, it becomes an integral. So I have the likeness of Passavant's theorem for Fourier transform, which says that if I were to compute the power in a signal, or the power that it has from minus infinity to infinity, it should be equal to 1 over 2 pi, the integral of the same thing in the Fourier space, is Fourier transform. Okay, this is a Passavant's theorem for Fourier transform. Okay. You notice that this thing becomes delta omega, and then in the limit when I let t goes to infinity, delta omega goes to 0, this summation just becomes an integral, and it just gets this. Okay? Are there any questions so far? And this is usually called the W in the textbook. Okay, W I guess is the total energy of a function. Okay? So you can see that if you have a signal if you have a signal function of t, f of t, the signal might look something like this. Say if you sing or you talk in a cell phone, your signal might look something like that. And what it says is that this signal has an energy. In order to find the energy in this signal, you square it and integrate over that thing. And it might have a Fourier transform. And if I were to find the Fourier transform of this signal, roughly speaking, it seems to have a DC component. Okay, it seems to have a DC component, which means that it does not time average to 0. So it will look something like this. Maybe that it has some high frequency component maybe, but then as the frequency goes 0, goes to infinity, it goes to 0. So the spectrum of this looks something like that. But this is a real value signal. If you have a real value signal, what do you know about its Fourier transform? Did you go through that in the last lecture? If you have a real value signal, if you take its Fourier transform, then I erased that formula. But, the goal of this thing is that f of omega is equal to 1 over 2 pi dt f of t e to the minus j omega t. Okay? If f of t is real, okay, if f of t is real, that means that if I were to take its conjugate value, it becomes itself. Okay, if I were to take the conjugation of this equation, it becomes itself on the left-hand side. But on the right-hand side, what happens? All these are real numbers. Omega is an integration on the real axis, so this remains unchanged. But if this is a complex number, if I take its conjugation, it becomes this thing. Okay? And then if I take the conjugation of this, I get this thing. Okay, f of t must be equal to that. Okay? But then, I say that this integral looks surprisingly like the first one. Why don't I do a change of variables? I do a change of variables by letting omega prime equal to minus omega. If I do that change of variables, then I would have d omega is equal to minus d omega prime, and this thing will become f of t is equal to 1 over 2 pi, and then the range of integration, if I do a change of variable as such, what happens to the range? It goes from infinity to minus infinity. But then I have a negative sign there. I just flip the sign back and flip these two things back to get rid of that negative sign. Okay? Because I did a change of variable, f of omega becomes f of minus omega prime, and then e to the j omega prime t. Now if I compare these two integrals, they're exactly the same, except for the fact that the argument is different. So I conclude that f star of minus omega must be f of omega. If I compare these two integrals, they're exactly the same integral, except I call this a prime variable, which is a dummy variable, and then I compare the two, these two must be the same. So if f of t is real value, its Fourier transform has to satisfy this property, which I think in the textbook they call it the Hermitian property. Okay, f of minus omega is f star of omega. Okay, because of that, if I were to plot this thing, if this is really complex value, I cannot really plot it because it's a complex number. So I better plot the magnitude of this. and not plot the phase. Okay, the phase might change, but the magnitude will look something like that. But because the negative frequency is just a complex conjugate of the positive frequency, what happens to the magnitude for negative frequencies? They should be the same, right? F of minus omega must be f of omega from this property. Okay, a complex conjugation does not change the magnitude of a number. You just flip it like this, okay, in the complex plane. So if I plot this fully, then I should have something like this. Okay? It's supposed to be symmetric, but I'm not a very good drawer. I cannot draw symmetric things, but you can imagine that it's symmetric, a mirror image of each other. Okay? Then, what happens is that
Professor,
yes,
how did you reason that f of omega is supposed to look like that?
why is this equal to
No,
that?
no. How did you reason that f of omega has that shape?
Oh, I
What are the
look at
reasons?
this and say it has a DC component, doesn't it?
Yeah.
So this term must not be zero.
Okay.
And it has some oscillatory component. So it must have some high frequency component. But then if I look at it, I do not see frequencies beyond 10 gigahertz. Okay, so it must be vanishingly small when the frequency gets very high. Okay, let's assume that if this is a voice signal, what do you think the frequency range would be? What kind of voice can we make as human beings? You must have learned that from a biology course. What is the voice range of us?
We're not doctors, we're
Um,
electrical engineers.
Maybe some of you are singers or pianists or something. What is the C key on the piano? How many hertz is that? Some of you might remember that. Does anybody remember what the meter C is?
Is it like 20 kilohertz?
20 kilohertz is the upper range of the human hearing.
2
We can hear from about 20 hertz to 20 kilohertz. Okay? And that is about what we can hear. Okay? So if this is a voice signal, this one is about 20 kilohertz times 2 pi. Okay, since this is omega. Okay? So
What is that in decibels?
what is that?
What is that in decibels?
Oh, that I do not know. Okay, you have to multiply by 10 and then take the log of the square of the magnitude of this. Okay? So one thing that you know is that this thing, this f of omega, is just the amplitude of f sub n times that number which I forgot. What was it? Is it
Omega over 2 pi.
equal to t? Right? That number is just t. Okay? So f of omega is just related to f sub n, and this represents the amplitude of the Fourier signal at e to the j n omega naught t. And this I call omega. Okay, omega is to the n omega naught, which is n 2 pi over t. Okay, that is my omega in this new Fourier transform space. And then whatever I have learned on Fourier series processing applies also to Fourier transform, because Fourier transform is also or just a limiting case of Fourier series transform. Okay, so if I were to have a LTI system, and if it defined by this frequency response function, which also is called a Fourier frequency response function is also called a transfer function in some textbooks. Okay, so what I have is that if I have a signal which can be written as such, e to the minus j omega t f of omega, okay, with a 2 pi somewhere. Okay, I think I have 2 pi somewhere there. Okay. Then if this is defined by this, just remember what you have learned about Fourier series applies to Fourier transform. What do you think the output would be if the transfer function or the frequency response is given to be such for a linear system? Y of t would be?
H omega with 2 pi times omega.
This is d omega. Yeah, d omega. Okay, it should be d omega e to the minus j omega t. And what should I substitute here? We will be just h of omega times f of omega. The same thing applies. Okay, because Fourier transform is just a limiting case of Fourier series expansion. Whatever you have learned for phasors, whatever you have learned for Fourier series applies to Fourier transform as well for a linear time invariant system. Okay? So we can have an h of omega that looks something like this. Okay? And if your f of omega looks something like this, and if this is 20 kilohertz, and over here is maybe 5 kilohertz times 2 pi. Okay, 2 pi f is with the omega. Okay, what happens to the signal after it goes through such a linear time invariant system with h of omega described as such? What happens to the high frequency components? They disappear, right? So you only hear the low frequency component. This is like your loudspeaker box. When you send your signals through your loudspeaker box, you only hear the bass, and you don't hear the tweeters, right? You don't hear the high frequency part, the tweeting part, right? Okay, so if you were to send this through here, and if I look at y of omega, roughly speaking, it will look something like this. Okay. Okay, it will look something like this. I didn't draw it exactly, but it's this multiplied by that give you that. This is called a low pass filter. Low pass filter signal. And you can call this the low pass filter. Okay, you can call this the low pass filter. And similarly, you can define other things. And you have learned about low pass filter when you were doing phasors and that kind of thing. The same concept applies here. You have low pass filter for Fourier transforms as well. And then you also have high pass filter. Okay, I need not have to elaborate on what it is. It's just something that lets high frequency signals go through. Okay, and then you also have band pass filter. Okay, this is high pass. This is band pass. So do you still remember how to design a low pass filter, a high pass filter, and a band pass filter with RLC circuits? You remember, right? Because you studied for your last exam. Okay. So you know how to do those things. And those things apply as well to Fourier transform signals. That means those things, at first you thought apply only to phasors, now apply to any arbitrary signal. Because it says that any arbitrary signals can be expressed as such. F of t can be anything. Okay? It can be anything. So, then let's talk about a signal bandwidth. What is a signal bandwidth? Say if we have a signal f of omega I can only plot its magnitude because I cannot plot the phase, or I do not like to plot the phase, then the signal might look something like this. I drew one for you that you did not like, because you questioned as to how I came up with that somewhat odd looking picture. So I just draw another one, which is more benign looking, and you probably wouldn't ask me the question as to how I come up with this picture. But it represents the signal with a finite bandwidth. A signal that has no extremely high frequency component. So one question that you beg to ask is, how do you define the bandwidth of a signal? Okay, how do you define the bandwidth of a signal? And you probably say that the signal has already dropped off at some omega max here, and then maybe minus omega max here. And I can say the bandwidth is roughly equal to 2 omega m or something like that. Okay? 2 omega m. But there are all more technical ways of defining bandwidth. Let's see how we can do that. More precise way to define bandwidth. Okay? So one is called a half power bandwidth. And that bandwidth defined to be a frequency omega such that the square of this signal and omega over the square of this Fourier transform at the DC value, and if this is equal to half, okay, breadth values drop to half, which means that the power has dropped to half. Okay, then the bandwidth is defined to be to the 2 pi b, and b defines the bandwidth. So b is equal to omega over 2 pi. Okay, omega is equal to 2 pi, maybe f max or something, over 2 pi. So the bandwidth is defined to be f max according to what I have over here. Okay? So the bandwidth of this signal, which drops to half its original value, is called the half power bandwidth. And it's also called the 3 dB bandwidth. Why 3 dB? 3 decibel is
110 log base 10 of 1/2.
right. If you take the log of half,
Times 10 is 3.
log of 2 is actually 0.3010. So if you multiply by 10, you get 3.010. So log of half max to minus 3 decibel. Okay, because if you were to take log of half and multiply by 10 is 3.010 minus 3. Okay, so the half power bandwidth is also called a 3 dB bandwidth, or minus 3 dB bandwidth to be precise, because it is the place where the signal has dropped to minus 3 dB from the value of 1 at the original point. Okay? And there are other definitions of bandwidth. You might want to define the bandwidth to be such that the energy in the Fourier space, this is calculating the energy in the Fourier space. We know that this is true by Parseval's theorem, that if you define the bandwidth to be omega, that if you find the energy within this omega range that is equal to Rw, W being the total energy. Okay, W is just the total energy R can be picked to be 90%, maybe 0.90, which is 90%. It can be 0.95, which is 95%. You can call this a 90% bandwidth or 95% bandwidth, depending on how you define this. So bandwidth can also be defined using this number, which is the percentage of the total power that is encapsulated or captured within this range of frequencies. Okay, this definitely applies to something like this, and in that thing there, I would call this omega and minus capital omega. And within this range, you have 95% of the energy or 90% of the energy. Okay. Okay. Let's see. Let's go to example 7.12. Exercise example 7.12. Maybe I don't have time to finish all the examples here. Let me just do example 7.13. Maybe I will have time for that. Keep example 7.12 and do example 7.13. So in that example, you are given a signal with power bandwidth that looks something like that. Okay. Of course, nothing looks that ideal. It's a textbook problem. So as to make life simpler for you,